Your time starts.
Okay, good morning everyone. So today we're going to be talking about our design project, which is this water filter pump that you see here, and we'll explain more about the physics and our design and the way we built it.
Now, before we start, we wanted to give you a little bit of overview of what this presentation is going to be like. So first we're going to start off by explaining what the purpose of the experiment is. Then we're going to go into why this is important on a global scale and the people that this impacts and affects. Then we're going to go into the design and how the design has changed throughout our project. Then we're going to go into the physics principles and how the physics principles have affected the design. Next we're going to go into the build stage and any issues and how we mitigated those issues that occurred during the build phase. Then we're going to talk about a little experiment that we did during our project, talking about the flow rate of the filter. We'll get into that a little bit more later. And then we're going to go and talk about the next steps of things that we wish we had more time to do and things that we would hope to consider if we're ever to do this project again.
So first the purpose. So the main issue we wanted to tackle is that more than 10% of the population in the world doesn't have access to clean water. And we feel like, well, water is a necessity of life. Everyone deserves to have something as water, but some people still struggle every day just get a clean water source. So we thought it was an issue very important to us, and we wanted to try and manufacture something that could help with that issue. And we also wanted to ensure that it was cost effective and inexpensive, so people in developing countries were still able to use this, and it wouldn't be worrisome for us having to get a lot of money for them to manufacture it.
So next we're going to be talking about the factors that affect this project and how it is important on a global scale. So first, there is societal perspective. This project allows those who struggle to find clean drinking water to be able to directly pump dirty water and convert it to clean water. A big important aspect of this is that the filter can actually be built with no prior knowledge. So it's very, very easy to manufacture. You can do it yourself at home with household parts, and it's very inexpensive as well. So this can be done by the afflicted people very, very easily. Next, from an environmental perspective, a water filter allows for a way to conserve water, as well as it does not introduce any harmful plastics into the environment and any other harmful materials into the environment through water runoff, etc. This plastic that is used for this water container is actually usually for household items that are usually discarded and end up affecting the environment. So this is a way almost to reuse those plastics, and it's a bit more environmentally effective that way. Economically, the construction of this filter costs less than $2. And we were hoping that the low-cost circuitry and the frame here could be delivered by charitable organizations who can give this to those who are afflicted, and the filter can be built by the afflicted people. So what we're really selling here is the design, and the product and what can be built at home is the filter.
So talking about our initial design, so this is the primary sketch that we had for what we wanted to do. So initially we had all parts stacked on top of one another. So we had the pump, then the filter, and then we had where you collect the water under it directly attached. It looked more like a manual water pump. So opposed to as you see now, which is right here, which is like an electric water pump, it would look more like a manual one with where you push down a valve. And it was also attached to a generator, so we decided to go with batteries in this one, but initially we had a generator that we were also going to build that we had attached to it so it could run through that. And the way the water would work with the time is we had valves to control the water flow, so when the filter filled up, one of the valves would close and another one would open at the bottom so the water could fall through. And the filter was also really small. It was about like the size of a tennis ball in our initial design. And that's just a picture of what it looked like without it.
Then this design changed and grew a little bit, and instead we changed our filter to an aquarium filter. So it wasn't a manual pump anymore. We got a big, strong filter from house items that we were able to find. The water intake was then managed by an Arduino instead. So instead of having time valves, the circuitry that we used was an Arduino. We decided to separate the filter and the pump, and as you can see here, that's something that we started to do in also the final design. And all the parts are smaller, or some of the parts are smaller than the initial design, but the filter is much, much larger than it was before. And you can see here, it's connected by the Arduino. You have put the pump directly in the water. It's an aquarium filter. It filters water it takes water through the tubing to the filter, and the filter allows the water to come into that bucket.
And so our final design, which you can see here, So we decided to have all materials attached to one another. So we have the base here, and the filter slides in easily through the hole there, and it gets locked in place. We also have the Arduino everything attached. We decided to make the pump size smaller, so it could fit on the side of the filter system, but also because we needed a smaller pump due to the amount of volts that the Arduino is able to output. Yeah, and the Arduino's attached filter, we actually put it on the back, so it was like more of a flush design. It's not directly all these wires out in the open. And then our filter was made with regular activated charcoal, sand, and gravel and cheesecloth filter. And this was mainly for the purpose that it was cheap, and people are able to build it with no previous knowledge. You just add layers of the different materials. And we wanted a more sleek and minimalistic design. As you see, saw from our design before, before this, it was all pieces all over the place and didn't really fit together. We wanted everything to be attached, so it was more, I guess, portable and better looking design. So that's the back of our design, if you can see, and it's really already on the back. And we also have the wooden panels on the side and top. Since we're dealing with water and electricity, and that can be dangerous, we wanted to prevent the water from seeping through. And then the front, as you can see there.
So now we're going to talk a little bit about the two major physics principles that are involved and helped us push through our design. And the first is fluid dynamics, and the second is circuits. So talking a little bit about fluid dynamics, the first issue that we encountered was that the pump here was not exerting enough pressure in order to move the water through the tubing. And because of that, we weren't actually getting the water flowing properly, and there's a little bit of an issue there. So in order to remedy this, we used Bernoulli's principle. And since the system is in a standing equilibrium, in order to increase the pressure at the intake end of the tubing, the height of the intake pipe compared to the output pipe was reduced. And that's why we built this structure here. So the pressure that was needed to exert up until here was not needed anymore, and we reduced that height, and it made a difference. And by that, we were able to get the water flowing. But we still had a little bit of an issue. It was slow, sluggish, and it wasn't what we envisioned in our head. So we thought of another way to remedy this issue. And to increase the pressure a little bit more, we decided to make a hole at the bottom of the bucket and inserted the pipe through it instead of just letting it dangle like you see here. Instead of letting it dangle, we inserted it through the bottom. And since the pressure of the fluid increases with depth due to the weight of the fluid above it, as shown in that equation, since we have water in here, this is the intake pipe, the pressure, due to the height with the hole at the bottom, allowed for more pressure in the water, and it allowed for the water to flow correctly. And that's the hole that we made, if you can't see it there.
So I'm going to briefly talk about the circuits. Pardon my voice. So originally, we had taken a pump for a hot tub and looked at it, and it requires something like 110 volts or something like that. So we were like, okay, we can't use that. We're using an Arduino, which on its own has a maximum output of 5 volts. So firstly, what we did is we ordered a pump, which is just attached here, which requires 12 volts, I believe it was. So even with the Arduino alone, you couldn't just see here. So this is the pump here. So the 5 volts from the Arduino was not going to be enough to power the pump. So firstly, we had to install an external power source. So we took two 4-packs of batteries, so 8 batteries, that's 9 volts, and connected that to our circuit. Secondly, we added a transistor to our circuit. So the transistor essentially, as I said before, the Arduino can only output 5 volts. This transistor allows for the Arduino to control circuits that have a higher amount of current and voltage than the Arduino's maximum output. So that transistor allowed us to be able to turn on and off the pump simply. And then I butcher this every time I say it, the potentiometer. This is essentially a variable resistor. So if you've taken computer science, you've used the resistors before to power the LED lights and whatnot. A variable resistor essentially has a little rotator on the front, and we can change the amount of resistance that's affecting the pump. And we just use that to be able to determine, okay, how much resistance do we need to allow it to work. Did I cover everything? I did. Okay, next slide, please. Secondly, the code that I wrote, I didn't put a snippet of the code in here, but essentially the whole code's running on a loop. And so the loop starts with an if statement, and it checks, okay, has the pump been running for the maximum amount of time that it's going to take to empty the bucket? And if it hasn't, then it continues on. Secondly, secondly, it runs for 3 seconds. So the pump will start running for 3 seconds, go, and it'll add that time to the maximum amount of time. Then it will sleep for 8 seconds, and that loop will just continue repeating until the maximum time is reached. I think I covered it all there. You're good.
So yeah, build issues. So obviously along the way due to time constraints, we had a couple of roadblocks in our way. So initially with the pump, as we described before, we had different sizes. At first we had the manual one, we had the aquarium / hot tub filter, and then we have this one now. And so the reason we switched them out was because the level of volts that were needed, that the Arduino could output. And then also the filter size was a major issue since we wanted to ensure that the water would pass through in a timely manner. And then the battery was fine enough power to allow all the water to go through and into the pump and have enough pressure. And design of the filter, we wanted to make sure that it was sleek and looked nice.
So that experiment that we talked about a little bit earlier, I'm gonna delve into that a little bit. So what we were looking at is the timing of the water filter. So the amount of water that it would take to fill up this chamber here and making sure that that would not overflow. So we ran an experiment where time to fill the filter was measured and time for the water to exit the filter was also measured. And based on these two measurements, a program was written, as Matthew explained, to shut on and off the pump corresponding at the rate at which water entered and escaped. So the overflow was a big issue that we incurred during the design, so we had to make sure to account for that. And to make a rudimentary estimation of what the amount of time that it was going to take to fill this chamber, we use this equation here, A1V1 equals A2V2, knowing the area of the tubing, knowing the volume of the chamber here, and also knowing the flow rate of the pipe, we were able to estimate how long it would take for the water to fill up this chamber. And using that, we were able to make a proper estimate. And that's what you're seeing right now. It's running and it's not overflowing. No, but it was running.
And yeah, we decided it was about 3 seconds running and then 8 seconds sleeping was enough for this to fill up, but then also sink enough so that it could fill up again without it starting to come into overflow.
Yeah, so next steps. Obviously due to time constraints, we didn't get to complete everything that we wanted to. So in the future, what we really want to hope for this is to find a way to make those products smaller and more portable. As you can see right now, it's a little bulky and big. And our whole thing is being able to deliver it to developing countries where they can use it like on a daily basis when they find dirty water to convert it to clean water. So we want to make it a lot smaller. We also want to make the design more sleek and cohesive, so everything's, there aren't parts everywhere, and yeah, just the size of it. And lastly, we had the idea to add a turbidity sensor, which pretty much just checks for the chemicals in the water, and there would be a sensor on the filter that would tell you what's in it. And so this was another way of checking how the cleanliness of the water, and we thought that would be a nice addition to our project. So thank you for listening.
Questions, anyone?
We also just wanted to mention really quickly that this is actually lake water that we're actually filtering right now.
You
So
guys
this is
can
like
go forward and see the demo.
yeah, if you guys want to come up, ask a question.
Water and everything.
Does it filter that fast?
Faster what?
Like, is that as fast as it goes?